Hello. In this lecture, we will revisit this paper. I will give an example on what it means to have two cultures in statistical modeling. These two cultures, since 2001, have merged, and um, so a lot of problems that are mentioned in this paper to some extent have been resolved in the statistics community, and in a way what we know today as data science or machine learning is a combination of the data modeling culture and the algorithmic modeling culture. Okay. So what is the data modeling culture? The analysis in this culture starts with assuming a stochastic data model for the inside black box. What is black box here? We always start with data, and we think of data as being generated by a black box in which a vector of input variable x, the independent variables, the features, the predictors, go in one side, and on the other side we have the response, or the dependent variable. Inside the black box, nature functions to associate the predictor variables with the response. So as we said before, there are two goals. One is prediction, and the other one is information. Prediction is mostly focused on just predicting what the responses are going to be to future input variables. So if you have a input variable which does not belong to the data you have, what is going to be the response? And information is more about extracting information about how nature is associating the x's to y's, which predictors have a stronger impact on the outcome, and then maybe use that information to recommend some domain-specific actions. The two cultures, the data modeling culture, makes an assumption about how nature basically creates the data, and then the question is, how can you find the parameters of that model? Now, the algorithmic modeling culture just assumes this is unknown and then tries to find some artificial method that is very flexible to fit the data. Okay. So let's go here. So let's just focus on this part again. This is essentially what data models mean. Statisticians in applied research consider data modeling as a template for statistical analysis. By imagination and looking at the data, we can invent a reasonably good parametric class of models for a complex mechanism devised by nature. So the example of Bayesian binary classification falls into this group. We do not know whether the measurements are Gaussian or not, but we assume that is the case, and there are reasons to believe that a Gaussian model is a good model, but there's absolutely no reason to assume it's Gaussian. Okay, it's unimodal, it's concentrated, so Gaussian might be a good model to capture the relationship. On the other hand, in the algorithmic modeling approach, data models are rarely used. For example, K-nearest neighbors is an algorithmic modeling approach, but linear regression is not an algorithmic modeling approach because linear regressions comes from the assumption that the relationship between the response and the predictors is linear, and there is some Gaussian noise around it. So what is observed is a set of x's that go in and a subsequent set of y's that come out. The problem is to find an algorithm such that for future x in the test, fx will be a good. Now let's see an example in R. Okay, so this is an R example where we generate data according to a binary data generating process, which I will go into. This is similar to the example you saw. So this is R Studio, and I use it to give illustrative examples. So what are we doing here in the first two lines? I'm just deleting any objects that are around, and then I'm clearing the console. Then I'm calling some libraries for which I will use, and you can look into each of these libraries to see what they are doing by going into packages here, and then you can just write down class. Then you have all the functions here, but let's just wait for them. We will get to them later. For now, I just set the seed to 1, so whenever I run this, because there's randomness involved, I just want the randomness to be the same, so it's reproducible, and you all get the same results. Here, we are setting the parameters. We're saying, okay, I want n training data points and 1,000 test data points. So in a sense, we are saying our data set consists of 100 data points. And since this is a study, we can generate a lot of test data points. So to measure the performance, okay, on the test data points which were not used to fit the model. N here is, well, n is a sample size, which is the sum of these two. We have two features. It's a basically in this simulation example, we have two features. So our X matrix, which consists of it's an n by p matrix, n rows, p features, and we just assign some memory to it. Q is 0.5. Q essentially is our pi1, the prior probability that the label will be 1, and pi0 essentially the probability that y will be 0 is 1 minus q. And then here we randomly assign zeros and ones to this vector y. So it's a binomial random variable, which is with probability q, 1, and n of them. Then what we are doing is this. We have a for loop. For every y, we see if it's 1, then we say, okay, then let the measurements, the predictors, the features follow a Gaussian random variable with mean 1. And let's just do this negative 1. So here we have two features. We don't have to use two features. I use two features because it's easy to illustrate. So if y is 1, the features will have mean 1, and there will be a variability of around 1. The standard deviation will be 1. This is R normal, so we are drawing a Gaussian random variable with p features, with p elements. So we are filling the rows of X with p elements, where each element, where the first element, p is 2, the first element has mean 1, standard deviation 1, the second element has mean 1, standard deviation equal. And if it's not, you don't need this. And if y is not 1, then the measurements will be in the negative values. Then we take the first n train observations, place it into x train and on y train, and then we take the rest of the observations, and then we create n test, x test, y test. These are the in KNN, these are the values of k that we like to test. So 2 to 20, 2 nearest neighbors, 3 nearest neighbors, 4 nearest neighbors. We're creating a sequence which goes from 2 to 20 and jumps 1 by 1. Here we take the number, how many do we have, and then we create a test error and a train error. So for each of these number of neighbors, we want to see what the performance is. Now here we have a for loop which goes over all these values, the k values, and KNN, KNN is a k nearest neighbor algorithm, which for each data point looks at what other data points are near it, and based on their labels will make a prediction. So we're giving it x train, we're giving it x test, y train, and ki, where ki will go over all these numbers. So we give an x train, y train, and then we say make a prediction on x test, and it gives us a prediction, y test hat. Then we are going to compare this with the true y test we have. We count how many are not the same, and then we divide them by how many we have, so we get the error rate. So this will be a number between 0 and 1. The closer it's to 0, that means it's better. And then we do the same thing for the training part of the data. Then we will print it out here. We say, okay, for this neighbors, this is the test error, this is the train error, and so on. Now, once we have this, we are creating a data frame. A data frame is like in R, is like a matrix where each column can have a different, so one of them can be numeric, the other column can be a string or categorical. That's a good thing, because here we're creating a data frame where we are creating one column for the trains, and then test, and then 1 over case, 1 over test. So let's just run this, and then it's easier to explain. So here what we are seeing is that as the number of neighbors increase, the training error, I mean, it goes up and down, but essentially here it looks pretty constant. So let's just go back here. How do we come down? Okay. Now I wanted to show you this one, this data frame, to show you what this is. This is what I'm creating here. So we have 3 columns here. Okay. There are 3 columns: set, inf, k, and error. Set is an indicator. It tells me whether this row is corresponding to the training set or the test set. Then we have the inverse k, because as we saw before, 1 over k is a measure of flexibility. So if k is small, then k nearest neighbor is very flexible. If k is large, then it's not very flexible. That's why we use 1 over k, so that if 1 over k becomes larger, we know that we are dealing with a more flexible model. And then we have the corresponding error. And then here we are plotting both the train error and the test error with different colors. And this is what we are getting. It's fluctuating. It doesn't look anything like what we saw before or what we expected, and this is okay. This can happen, and if it happens, then this is just how it looks. But what we can see is that the test error is minimum here. So if we wanted to achieve the lowest test error, we probably would have picked the k corresponding to this 1 over k. So let's and then the rest here I am looking at basically what k leads to the lowest test error, because that's what we care about. It's 15. And then here I'm creating a grid over all the possible values, just splitting it and then doing KNN and then doing a plotting. Let's just illustrate this here. That's better. Okay. This is our training data. As I said, if the label is 1, the mean should be 1 and 1. So this is 1 and this is 1. So the data is centered here. It has a standard deviation of 1. That's why it's scattered around here. And the same about -1. So to make this a little bit more visible, let's make this 0.2, and let's just run it. You see the data has become completely separable. So when we say data generating model is this sort of thing. You assume the data is 2 clouds. It has 2 classes, so it's 2 clouds. And they are concentrated around those 2 centers. Now here you see there is no overlap, and this is the predicted probabilities of label 1. So here is you see that the lighter color is 1, darker color is 0, and these are the predicted labels. So essentially KNN is saying, okay, draw a line here. Now let's play a little bit with this, and let's make this bigger and this other one smaller. Now the 0 label is more scattered, the 1 label is less scattered, and then the k nearest neighbor is just going around here. Again, what is k? K will be different each time. So maybe we like to, it would be nice to plot it, to print it. Optimal k is this each time. K with smallest test error is k optimal. Because depending on the data, this number changes. Is 2. 2 nearest neighbors. Which is not surprising because there's not much overlap between the two clouds. I believe if we add more, if there's more overlap, then this will be a little bit trickier. So let's create more overlap, add more variability to the -1, the 0 labels. Well, it's still 2. Let's look at it. Okay. Now you see things are changing. Actually, I think less overlap, but let's see. See, the training error with 2 is 0, and then it slightly increases. So let's do this. This 5, this 5, and let's see what we get here. So now we have a bigger cloud going over and surrounding a smaller crowd. And this smaller crowd is trying to draw a boundary around it so it can separate itself. And the optimum k is still 2. So let's see, what can we do something more interesting here? And just give me 1 second. Okay. Now this is again around 1 and 1, which is here, with a standard deviation of 1, and -1 and -1 standard deviation of 2. And this is the predicted labels. Let's look at this k with the smallest test error is 6. Let's look at this plot. Okay. So as you can see, when we set the U shape, you see here there's this U shape. Essentially, the test error is minimum somewhere in the middle, not in the very flexible regime or the less flexible regime. And the train error, even though it goes down and up, essentially there is this downward trend, and obviously there's always going to be a little bit of variability, but just pay attention to the general trend that it's going down, and here it's going down and up. Okay. Now here we have a very specific data generating model, and we know how to treat this using a Bayesian classifier. We did the math, but we did not use that model at all. We just treated it as something we don't know where it's coming from. And we use the k nearest neighbor approach, which is an algorithmic approach to classify these points. Now, another thing I want to draw your attention is that in the math that was presented in another lecture, the standard deviations were equal. Here we are not making them equal. Everything, all the math that we did, all the Bayesian classifier that we explained was based on the assumption that the variances are the same. If the variances are not the same, that math would not be valid. So again, that's another limit of a data modeling approach. But the data modeling approach, despite all its criticism, has led to a lot of success stories. So it's a two-sided story. I guess both approaches should complement each other. That's how I see it personally. Okay.